While most people wouldn't consider the crusty exterior of an oyster to be particularly beautiful, opening up this craggy case might reveal an exquisite jewel nestled within. Yet, despite their iridescent colors and smooth shapes, pearls are actually made of the exact same material as the shell that surrounds them. Pearls, urchin spines, the shells of mussels, snails, and clams, even coral, all these structures are made out of the same chemical compound, calcium carbonate. So how does this single ingredient form such a vast array of materials? Calcium carbonate, or CaCO3, is common on land and even more bountiful in the sea. The Earth's crust is rich in calcium, and over millennia, these deposits have seeped into rivers and oceans. This is especially true near hydrothermal vents, where hot seawater mingles with calcium-rich basalts. Meanwhile, when carbon dioxide in the air interacts with seawater, it eventually produces dissolved carbonate. Every year, the ocean absorbs roughly 1/3 of our carbon dioxide emissions, adding huge quantities of carbonate into the water. It's no surprise that sea creatures have made use of these abundant compounds, but the way calcium and carbonate are woven together into various shapes is surprisingly artful. Let's return to the humble oyster. Like many aquatic mollusks, oysters start life as exposed larvae and quickly get to work building a protective shell. First, an organ called the mantle secretes an organic matrix of proteins and other molecules to construct a scaffold. Then the oyster filters the seawater, drawing out calcium and carbonate to combine them into its building material. It lays this material over the scaffold, which is covered in charged proteins that attract and guide the calcium carbonate molecules into layers. The specific arrangement of these protein scaffolds depends on the mollusk species and their environment, accounting for their vast diversity of shell shapes, sizes, and colors. Mollusks carefully control all components of their calcium carbonate creations, even manipulating CaCO3 at the molecular level. Using special proteins, mollusks can produce two crystal structures out of CaCO3, calcite and aragonite. Both of these compounds have the same chemical composition, but different qualities due to the way their crystal lattices are arranged. Calcite is the more stable of the two and less prone to dissolving over time, so most mollusk shells have a sturdy outer layer of calcite. As the slightly more soluble molecule, aragonite can better adapt to more or less acidic environments, so most mollusk shells have an interior layer of aragonite to maintain their internal pH level. But one form of aragonite is stronger and more versatile than the rest: nacre. Mollusks make this special material by placing successive layers of aragonite interspersed with proteins. These layers are stacked like hexagonal bricks, each surrounded by other organic material that directs their orientation. The uniform layering and brick-like structure of nacre is key to its signature iridescence. The layers are similar in thickness to the wavelength of visible light, so the light reflecting from its interior surface interferes with the light reflecting from the outer surface. When particles of light strike the nacre, they bounce around its multi-layered crystalline structure in a cascade of shifting rainbows. But nacre isn't just pretty, it's one of the strongest and lightest biomaterials we know of. And it's not just oysters that produce it. In fact, numerous mollusk species deploy nacre as one of their primary defense mechanisms. If an intruding parasite or even a stray particle of sand irritates the mantle, the mollusk will coat the offender in nacre-producing cells to form what's known as a pearl sac. These cells wrap the threat in layers of proteins and aragonite until eventually the cocoon completely absorbs the invader, dissolving the threat into an opalescent sphere of nacre. This defense mechanism is our leading theory for mollusks making pearls, transforming everyday intruders into timeless treasures. Another gem that begins its life as something completely ordinary is the opal. This rock starts as water and then transforms into the most colorful gemstone on Earth. So how does this happen? Dig into the science of the opal's vibrant colors with this video.